Welcome to lecture 13, the NPTEL online certification course on bioreactors. We are towards the end of module 3. We had assigned a problem in the last class. We will work that out, and with that we can complete module 3. The problem statement reads as: processed fungi are good biosorbents for toxic trace metals, and thus they can be used to remove chromium, mercury, cobalt and others from industry effluents. A suitable fungus needs to be produced at 500 gram per hour for the above purpose. That's the production rate. The growth limiting substrate concentration at the inlet of the chemostat to produce fungus is 50 gram per liter. The fungus follows monod kinetics with the maximum specific growth rate being equal to 0.5 hour inverse. The substrate concentration that corresponds to the half maximal growth rate is 1 gram per liter. It is aerobic growth with a yield, cell yield coefficient from substrate of 0.5. That is why x/s is 0.5. Find the minimum size of a chemostat needed for the above for a given inlet flow rate. The solution is as follows. We will ask our same questions and try to answer them. What is needed? The minimum size of a chemostat needed for the above given conditions for a given inlet volumetric flow rate. What is known or given? The production rate is 500 gram per hour, that is given. The maximum specific growth rate is 0.5 R inverse. The Ks is 1 gram per liter. Yxs is 0.5. All these are given. And also Si, the inlet substrate concentration in the feed, is 50 gram per liter. Monod kinetics for growth is given. Now, how do we connect what is needed to what is given? If the volume needs to be minimized, we need to be operating at the maximum productivity, Rm. Okay, that's what makes sense. Only if the productivity is maximized can the volume be minimized to get the best out. Our inlet flow rate F is fixed, and the dilution rate is defined as F by V, or the volume of the reactor is F by D, just transposing this. And so to minimize V, we need to maximize D, because V equals F by D, right? When V is minimum for a constant F, D has to be maximum, only then V will be minimum. So we need to find essentially dm, which will also maximize the productivity, because dm into mu m and so on, mu m into x was our productivity. So that will also maximize productivity. We have already derived our dm as mu m times 1 minus square root of Ks by Ks plus Si, that we have already derived in our previous lecture. Now, if we substitute the values that are given in the problem, we will get dm equals 0.5 is mu m, 1 minus Ks is 1 gram per liter, and Si is 50 gram per liter. This is the square root, and if we calculate the value, it will turn out to be 0.43 R inverse. You need a calculator to do this. If we know F, we can find Vm, the minimum size of the chemostat. We don't know F, but we know that the productivity is 500 gram per hour. Okay, from this, we will have to somehow find F and thereby find the minimum value of the reactor volume. And we also know that Rm is F times Xm. This is where we get the relationship between F and Rm. Rm is F times Xm. Xm is the outlet cell concentration at maximum productivity, right? We need Vm, we know Rm, so we are trying to find F and therefore Vm by using Rm. We also know the yield coefficient. We, we know that the cell concentration is y-axis times Si minus S. Therefore, Xm is, if you substitute the conditions for the maximum, then we would get Xm here. Maximum cell concentration, we get Sm here. So, y-axis times Si minus Sm. This is the condition, this is the substrate concentration in the outlet, which corresponds to the maximum cell concentration Xm, maximum productivity. To find Sm, let us use the relationship between D and S. I hope you are able to follow all the interrelated aspects. That's an essential feature of many problems, and that's what takes time to develop, to be able to see the various connectivities. So mu m equals Sm, mu m Sm by Ks plus Sm is dm. So mu m Sm is dm times Ks plus Sm, just transposing, and just collecting all the common terms. Sm into mu m minus dm equals dm times Ks. So Sm equals dm Ks by mu m minus d. Let us do the above step by step through substitution of the relevant values for our situation. Sm here, dm Ks by mu m minus d. Dm, what we found from the earlier case, was 0.43. Earlier calculations 0.43. Ks is 1. Mu m was 0.5. Dm was 0.43. This turns out to be 6.14 gram per liter. So Xm, from Sm we are calculating Xm, and therefore dm and so on. That's the way we're going to go about it. So Sm was 6.14 gram per liter. Xm is Yx times Si minus Sm. Just substitution of this, we get 0.5 into 50 minus 6.14, 21.93 gram per liter. And Rm is F times Xm. We'll come to this in a little bit. It came a little early, doesn't matter. Rm equals F times Xm. So Rm is 500, F times 21.93. F equals 500 by 21.93, that's 22.8 liters per hour. So the corresponding minimum volume is F by dm, right, from the definition of the dilution rate. We said to minimize V, we'll have to maximize M. We have found out the maximum dm as 0.43. We went through all these steps to get F from the productivity as 22.8. So 22.8 by 0.43 happens to be 53.02 liters. Okay. So this is the minimum volume of the chemostat for the given set of conditions in the problem. Right. Okay. When we meet next, we will continue the course. We will start module 4. See you then.